In our previous lessons, we saw that if direct substitution into a function leads to an indeterminate form, we can use some strategies to find a function that's equivalent everywhere except for that point. So when x approaches c, in either case, they both reach the same limit. In a case like this, we use the strategy to find factors and divide out like factors. We also saw how we can multiply by the conjugate to rationalize the numerator. In this lesson, we're going to wrap up AP Calculus topic 1.6 by discussing the squeeze theorem, also known as the sandwich theorem or the pinching theorem. In this squeeze theorem, say you have some function h of x, where as x approaches c, the function approaches some limit L. Let's say you have another function, we'll call that g of x, and for that function, as x approaches c, it also approaches the same limit. In this case, g of x is less than or equal to h of x. And if we have some function f of x sandwiched or squeezed or pinched between these two functions g of x and h of x, because the limit of g of x as x approaches c is equal to the same limit as the limit of h of x as x approaches c, we can then say the limit of f of x as x approaches c has the same limit. On the AP exam, you usually see the squeeze theorem when you have a problem that asks you to evaluate the limit of expressions that contain sines and cosines. A classic example looks something like this, where we're asked to find the limit of x squared sine of 1 over x as x approaches 0. Some students will see this and try to apply the product property of limits, saying the limit of the products is equal to the product of the limits. But you can't do that here because the limit of sine 1 over x, as we saw in the previous lesson, does not exist. The function sine 1 over x looks something like this, and oscillates more frequently as you get closer to x equals 0. So the limit does not exist. So if the limit of one of the component functions does not exist, you can't apply the product property of limits. Instead, we're going to use the squeeze theorem. You want to recognize that sine 1 over x is in between 1 and negative 1. And that's because sine of anything is between 1 and negative 1. Now let's multiply this inequality through by x squared. So we get negative x squared is less than or equal to our function, which is less than or equal to x squared. The graph of x squared looks like that, and the graph of negative x squared looks like that. You may not know what the graph of x squared times sine of 1 over x looks like, but we know in some open interval about c, in this case 0, all three of these functions have the same limit, which is 0.